Okay, so today we're going to talk about topic 7, which is equilibrium. So we've talked about kinetics, now we're moving on to equilibrium, but this is all going to be related eventually. So we're going to talk about what it means for a system to be at equilibrium. Let's take a look at this graph. This is concentration versus time. You can see that the red must be a reactant because it's decreasing, and the blue must be a product because it is increasing. And at some point, this kind of levels out. So it's not that this red line, our reactant, goes all the way to 0. It's that it levels out. And when it levels out and remains constant, we're at equilibrium. Okay, so the general definition of equilibrium is when the forward and reverse rates of whatever process are equal. So let's look at some examples. Okay, phase changes. When you're right at the boiling point of a liquid or the freezing point, you actually have an equilibrium system potentially going on. Okay. So if we're right at 100 degrees Celsius and it's a closed container, we're going to have equal rates of boiling and condensation. So this is in a closed system, can't just all evaporate. And so you'd have this rate, however many molecules are going from a liquid to a gas per unit time, is equal to the number of molecules that are going from gas to liquid per time. Okay, so there's no net change. Okay, freezing and melting. Well, you could say it in terms of molecules, or you could just say that the rate of melting, going from solid to liquid, is equal to the rate of liquid to solid, freezing. So again, you don't see any net change. But things are still happening. We just can't see it. Okay, in terms of dissolving, now this is for things that are just slightly soluble, or if you have a solution that's completely saturated and maybe there's a little bit of whatever compound sitting at the bottom of your beaker. But the molecules and ions are dissolving and coming out of solution, precipitating at the same rate. So these are all examples of physical equilibrium. Okay, here's another example of physical equilibrium. In terms of chemical, you could have this. Okay, let's say we have the reaction of hydrogen and iodine forming HI, hydrogen iodide. Okay. Well, we have this graph, and notice that in this scenario, we start with H2 and I2, and it decreases and we form HI. And then in this graph, we start with HI and we form H2 and I2 because this is a reversible reaction. All of our equilibrium reactions are going to be reversible. Well, and for both of these scenarios, at some point, the hydrogen iodide and then the two elemental versions, they level out in terms of amount. And if you look, it's the same place on the graph, regardless of how they started. So in a chemical equilibrium, we have the forward and reverse reactions that are happening simultaneously and at the same rate. So you need to be able to explain some of these characteristics of equilibrium. First off, equilibrium is dynamic. What that means is that the forward and reverse reactions are still occurring. We have not come to some static place. It's just not happening on a scale that we can see. Now, a second condition here with equilibrium is that it's achieved in a closed system, meaning there's not an exchange of material with the surroundings. If we have a pot of water on the stove and there's no lid on it, it will boil and evaporate off, and then we'll have no more water. But if we keep a lid on it, we can have boiling and condensation happening all within that pot because the water's not escaping. You can get some real hot water. Okay, the concentrations of reactants and products remain constant in equilibrium because we've got equal rates of forward and reverse reactions. Now, at equilibrium, there's no change in macroscopic properties, meaning things we can see with our eyes, like color and density. Why? Well, those are dependent on the concentrations, which have now leveled out. and that should say do not, there's a not over here, do not reflect what is happening at the molecular level. And lastly, equilibrium can be reached from either direction. So if the conditions like temperature and pressure are the same, then the same mixture of reactants and products will result, whether we start with all reactant or all product or a mixture of the two. And we'll see how that works in our next lesson. So our last thing is our mastery check. Here you go. What is always correct for a reaction at equilibrium? You're going to use Google Forms to fill this guy out.